Hello, this is Bronya. Welcome back to my webinar about JavaScript, and let's continue with functions. There is something in programming language that is passing variables by reference or by value. So what does it mean? When you have a memory where variables are stored in memory in your computer. So this is a variable, and this variable has certain value. Let's say 51. So the 51 is the value of this variable. And let's call the variable, let's say I. So that's a variable I with the value of 51. Where the variable sits in the memory, the address of the variable in the memory is called a reference. Why is that important? Well, it's important because how you pass variables. The primitives, which are these, you pass by value. So when I'm running this code, A isn't I, it's not the same variable. It becomes a new variable, and the A becomes 5. A becomes 5, it increases to 6, it is returned. J becomes 6, I is still 5. The I didn't change because when I passed it to the function, I didn't pass the I created a new one. So I created a new one, it used to be 5. I create a new one in a variable, it's called J, and it gets assigned the value of 5. Well, it's called A, I'm sorry. Gets assigned a value of 5, then it becomes 6, and it's returned from the function. This is discarded, and the value it's returned from function and assigned to variable J. This gets discarded. So those are two distinct variables. This is how it works. It's called passing by value. The value gets copied. We will see later on that objects actually are passed by reference. So when you pass an object to the function, you pass the object itself. although I assigned I to j and I increased j, I remains 5, j becomes 6 because I was copying the value. I didn't assign it to become the same thing. They're distinct in the memory. So this is how it looks in memory. It's not like this. Okay. Let's discard this, discard this, discard this. Like this is created, and then it says, okay, this is becoming j, and it points to the same value. Both of those identifiers are pointing to the same value. Now, two distinct are created. This is called passing by value, and it's working for primitives. Value and reference become interesting with something that is called closure. It has bitten a lot of people today, respective asses, if you don't mind. So, how it works? What's closure? How it works? Let's define a function. Define a variable. And let's define another variable. This way, by the way, I want to show you something first. I talked about the fact that function is just a regular variable, so what I can do is have a function and simply return it. It's value. So I can do and x is a function. So x, if I do just x, x is a function. So I can actually run x, and when I run x, I run the function. So what happens now? Well, it's working. Well, one may think it should not be working, because when I exit the function, this scope should be discarded. So the word should not exist because I run this. So this ends, word get discarded, this getting returned, and x is called after the run ended. But the word still works. This is called closure, because this function creates a scope, chain of scope. We talked about it. So it says, okay, I need a word. I don't have a word. I have a word outside. So it's chaining the scope. And you cannot just discard scope that's in the middle. You have a global scope then you have a scope of a function run, and then you have a scope of this. It's called anonymous function. If it doesn't have a name, it's called anonymous function. So you have a global scope, you have a run scope, and you have that anonymous scope of the anonymous function. And it's chained like this, as I've said lexically, where it's defined. The run is defined in a global scope, so it's pointing to the global scope. The anonymous function is defined within the run, so it points to the run scope. So when I exit, this scope should be discarded because I've exited the function. But there's a scope pointing to it, so it doesn't get discarded, and this variable still works. I can't do this. The word doesn't exist in the global scope. It exists in this scope, but this scope ran and get discarded. It no longer exists. I cannot do this. It doesn't exist in the scope. But I can only discard what's on the top of the stack. But since this creates a scope that's chained to the upper scope, this scope cannot be discarded. It must exist. And this is called closure, when the function closes around its outer scope and all of the scopes in the chain. So until there is a scope that has to exist, which is here, because the function exists, so the scope for the function must exist so it can run, everything that's in the scope chain must exist. That's closure. And closure can cause a lot of issues. I don't have to do this. Okay, so what does it say? Okay, let's go around. Console log loop. You can do this way or this way. If you do it as a separate parameters, the console log function will simply concatenate everything, which is the same as if you do it with the one parameter that is already concatenation. So I go through here. Let's not run this. Yeah, so I go from 0 to 2, and if I is 1, I create a function that logs out the I if I is 1. So if I run the function, I can assign the function to anything. So this should be 0, 1, 2, 1. Well, no, it's actually 0, 1, 2, 3. Why? Well, because when you're working with closure, you're not working with the value. We talked about passing by value, but you're working with the variable itself. This isn't a new variable. This is a value. So this is not a new variable with the same value, which would be 1. It's the variable itself, which means when this ran, it goes 2, becomes 3, this fails, I becomes 3. So when this ran, it runs this function, which is, let's output 3, because we're working with the variable itself, not with the value. This has bitten seriously a lot of people. How closure works in a cycles. They usually think, okay, this is gonna work because I'm working here with 1, so this is gonna be 1, but it's not gonna be 1 because we're working with the variable. And the variable creates closure. So how can I fix that? Why? If I put var here, by the way, it still doesn't work. Still works wrong. Why? Because this gets hoisted outside, and it becomes this global I variable. If I do this, it only applies to the block. For every block, a new variable is created. So it's working because the variable I is here. It belongs to this block. For every cycle of the block, the I gets recreated. It's a different value. It's a different, not different value, not just different value, it's a different variable. It's not the same variable. In this case, it's the same variable, the variable I, because it's declared and it belongs to all of this. In this case, a new one gets created. There is another way how to fix that. So if I comment this, this doesn't work. When I do this, it works. Well, that looks weird. So what is it? This is function expression. It's not function declaration, it's function expression, because it doesn't start with the word function. It becomes function expression. If I do this, this is function declaration. And I cannot run it. It's a declaration. I cannot do this and run it. That's that doesn't work. 2, 3, some. How does it work? Yeah, it doesn't work. This ends here. This is. It works sort of like this. It doesn't work. It doesn't run. In this case, it's actually passing an error because, well, this is nothing. So this is how JavaScript interprets it. This actually is something. It's the global operator. It just doesn't do anything. It just doesn't output anything, but it's a global operator. It's the global operator. It's not running the function. If I do this, the function sum becomes an expression. There should be probably a plus b. It becomes an expression. An expression can be ran. So I can immediately run it with the values 2 or 3. This is also valid, by the way. This also works. I suggest you stick to this, so you enclose the function and pass the parameter behind it. A lot of people are used to do this. It was considered like better because there's a at the beginning, there's one at the end. This is slightly better for, well, this very reason. If I use the fat arrow, this will work. If I use the fat arrow, this doesn't work. So this is, by the way, called IFI, immediately invoked function expression. Immediately invoked function expression, IFI. So let's look at it here. So what I do here is I do this function and I immediately execute it. This is the function expression, and I execute the function with this parameter. So this returns a function. This is a function that returns a function, and I can execute it with some parameter. Why it's not okay. It's the function. I can say x equals the function. If I run x, I don't return anything from here. Okay, I would have to return something from it. Would have to actually return f, and then I can run actually x, and it does what it's supposed to do. console. So this creates a function using a function expression, and this runs the function. And although I didn't change this one, since I'm passing variables by value, not by reference, this is the same as this one. But this is different. This is a variable, this is a parameter that belongs to the function. It's sort of within the scope of the function. The same way as I can use things in sum I can do that. They are already declared. They belong to the function and they belong to the scope of the function. So I can use them within the function, I cannot use them outside. They're not defined. So they become part of the function scope. So this I is a different I, it's the shadowing. It's the different variable. It's sort of like I would declare it here. Sort of. It belongs to the scope of the function. So I'm evaluating this function with the value of 1. The parameter I is 1. And since it's passed by value of a different variable, not the same variable, well, this becomes 1. In this case, I'm still working with this variable. So although this gets assigned only if I is 1, the variable loops all over again. And at the end it's 3. So when I'm calling this function, I'm working with the variable itself. When I do this, I'm creating new variable for each cycle. So it's always a different variable, which means it stays the same because the variable that starts with 0 is discarded at the end, and I'm working with new one. And in this case, I'm actually not working with this I is not this I. This I belongs to the function, and the function is called with the value, not the variable reference, but the value. And what we use for that, what we can use for that, is something called immediately invoked function expression, also known as IFI. IFIs are very useful. It doesn't look like this. This looks weird. Why? Like why? But IFIs are very, very useful. I have two scripts here, before and main. Let's do it this way. Script console log and variable myvar. So this will return an error because myvar doesn't exist anywhere. Now it's 11. But let's say I want to work with the 10. I don't want to work with 11. I want to work with the 10. But since it's a global one expression execution context, all those scripts are running within the same context. It may cause a problem because you may have several scripts included in your project and they all running in the same execution context. And there can be collision, there can be issues. So let's say, let me put it this way. My var has already been declared. Yeah, let's leave it like this, why not? The collision is going to happen here. I can use something like let here. That's going to work because it's not going to work. It's already been declared. The let allows only one. So there's a collision here. So I'm using some variable in some script. I execute some other scripts. They may have the same variable of the same name. They may use it for whatever they want. But now you have to like figure out, okay, now I'm including some scripts. What do I do? Do I have to like check for every variable that I type whether it's not colliding with any other? So what we do is we usually enclose scripts in immediately invoked function expression. Or like this, it's pretty much the same. And now it works. And it's actually 5. Although I have reassigned value twice, it remains 5. Why? Because this creates a new scope. This creates its own scope. This is solvable with easier way with modules, but modules are way too complicated for now. But the thing you should remember is just enclose everything in immediately invoked function expression, and there will be no collision. Sometimes, well, what if I need something that I create in var use somewhere else? There is a way to do it. When we get into objects, this is the global object. We talked about the global this, the window. It exists everywhere. I just create a property on it so I can use it outside. So there is a way to export, quote unquote export. As I've said, this is much better done with modules, but not going to talk about it right now. So there is a way to export stuff, but you export stuff explicitly. You explicitly say, I want to export this value, this object, this function. And when you enclose it in the immediately invoked, in the IFI, there is no collisions. You're sure there can be no collisions because And everything you do stays in, doesn't bleed outside, and there cannot be any naming convention. Any naming collisions because you're creating a new scope. I hope it makes sense. So the immediately invoked function expression is very useful. Since it's a function expression is something that doesn't start. Well, this would fail, of course. It doesn't start with a number, with the word function, or like this. So okay, uncode. Yeah, of course, I don't have the blah define. This should work perfectly fine. Yeah, this still works. I don't know about the arrow function. Apparently it breaks down, it doesn't parse correctly. But this is an expression, it doesn't start with the word function, this is an expression. It turns this, which will fail, because it's a declaration to expression. It doesn't matter. Mostly we use simply this. So those are closures, ifs, reference by value, passing variables by reference, or passing variable by values. Get back to this. So we know this doesn't work as we would like it to work. Why is there a 5? Okay, it's from here. This is going to work as expected. Again, because we're passing values to the function. So the create functions actually create functions. But this is passed. This is a closure, by the way. This is a closure. There is a closure here, because this param is not defined here. It's defined as this scope. But since the function exists, it encloses this param. But the param is here passed by value. We're not working with the reference to the variable, we're working with the value of the variable. So this is passed. There is one, number 1 is passed, number 1. This creates a closure around number 1. I know it's quite complicated, but I hope it makes at least some sense. Okay, the last thing I want to talk about now with functions is recursion. We're gonna talk about this later. Recursion. What is recursion? Recursion is when a function calls itself, or when you have function A that calls function B, and you have the function B calls function A. So it's calling itself. So let's design a function like that. Do you know Fibonacci sequence? Fibonacci sequence is one of the most famous mathematical sequences, and it goes like this. 1, 1, 2, 3, 5, 8, 13, 21, 34. I hope it's correct. It's sort of a mathematical expression of something called natural growth. You see this sequence expressed actually in the nature of how, for example, shells grows in slugs, etc. Doesn't matter. What matters is that the first value is 1, second value is 1, and every other value is sum of the two previous values. So the third value would be 1 plus 1, it's 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 3 is 13, 13 plus 8 is 21, 21 plus 13 is 34. This is Fibonacci sequence. Here you see a spiral actually based on Fibonacci sequence, and it's in Pythagorean triangle. This is Pythagorean triangle if you know something about combinatorics, or it plays the role in combinatorics, it plays the role in how you work with a plus b squared, a plus b to the power of 3, how it computes. That's Pythagorean triangle. It's really very famous sequence. So let's create it. So the one way would be somehow try to analyze. Let's say we wanna this 2, 3, 4, 5, 6, 7th value. So we would somehow have to compute the values. So how can we do it? Let number 1 equals 1. Let number 2 equals 1. We start with that. Let partial equals 0, and let count, we want a 7th value. So how do we do it? While count this, we want to do it 7 times. We want to do it 7 times, so we go from 7 to 0, and we say partial equals n1 plus n2, and we say this is the first, this is the second one, this is the next one. In this case it would be the third one. And then we need to turn this into the previous, this into the second. So we say n1 equals n2, and n2 equals partial it's 31, 2, 3. This obviously gave me some let's try it like this. So let's figure out where the problem lies. Okay, the problem lies in the fact that I already have the first 2 here. So now I'm counting the next 3. 1, 2, 3. Okay, so when I had 7th, 1, 2, 3, 4, 5, 6, 7th. So what I can do is do this. If count equals 1, let's turn it into function. Fibonacci let's put it like this. Fibonacci count. Okay, if count equals 1, return 1. If count equals 2, return 1. Count minus 2 because we already have the 2, and return partial. So the third one is actually 2. The seventh one is 13. 1, 2, 3, 4, 5, 6, 7, 1. The ninth one would be 34. The 150th one would be, well, really big. Let's get 15th, 610. Okay, that works. How does this work? How does this work? As I've said, I'm just okay. This should be like this belongs here, by the way. Of course. Okay. So this is a Fibonacci. How it works, again, as I've said, there's a sequence 1, 1, 2, 3, 5, 8. So at the beginning, this is N1. Come on. 1, 2, 3, 5, 8. This is N2, and this becomes a partial. It's N1 plus N2, so this is this one. Then we need to compute this one, which means we need to do this. We need, in this sum, partial equals N1 plus N2, we need to sort of shift it. So we say the N1 becomes N2, the partial, the N2 becomes what's in the partial, and we're computing a new partial from here, which becomes this one. So we're sort of shifting the values to the right. Now we say we've computed the partial, which is 3, and we say N1 is what's in N2, N2 is what's in partial. I hope it makes sense, but it looks sort of weird. But what Fibonacci tells us? Well, Fibonacci tells us that number with the index of x equals number with the index of x minus 1 plus number with an index of let's say f. This makes perfect sense. We just know that fib1 equals 1 and fib2 equals 2. So this is what Fibonacci tells us. First Fibonacci number is 1, second Fibonacci number is also 1, third Fibonacci number is second plus first, fourth is third plus second. This is how Fibonacci is defined. Okay. $13. 34. Okay, so how does this work? It works. It works because this is how it's defined. So this is how it computes. So let's start with the Fibonacci of 3. Let's start with a slightly simpler function. Start with this. Three to 1. Yeah, it should do 3 to 1. There's no initialization phase. Param, we start with 3, so we print 3, it becomes 2. This is valid. Let's print 2, it becomes 1. This is valid. Let's print 1, it becomes 0. This is not valid. Prints. Let's print nothing. Which has happened? Why is... I don't want this here. How do I turn it off? Oh, wait a second. This... What the hell? Windows. Okay. Thank you. Okay, does it work? Should work. Oh, unexpected end of input. Lacking this works. So how does this work? It's again recursion. So when we enter this function for the first time, we create a new stack where param is 3. This is valid. We run the console log and we run the same function with the param -1, which is 2. So we run it with the 2. This works. And we run it again with the param 1. It still works. And we run it again with the param 0. This skips. So this is working, but how? What happens next? Okay, there's a bunch of ins, bunch of outs. Because the execution context, it's the execution context is created over and over again. but the execution context continues when the function ends. So when we start this with number 3, it goes here, it prints out 3, it goes here, from here it turns to 2, it prints 2, goes here with the value of 1, prints out 1, it runs this with the value of 0. This doesn't happen, so this out 0 happens. But then this function ends. But we ran the function from here with the param 1. So it prints out 1, ends, but we ran it here with the param 2. Let me paint it so it's slightly better. So first we ran the function that's, this is a function that's, with the value of param 2. With the param equals 3. Saying nonsense. This is how we run the function. Then we ran the same function and we pass to the function param equals 2. This is this. So this param becomes param minus 1. So this evaluates from 3 to 2 and we're running the function with the 2. Then we run it with 1. Come on. And this works, we output 1, and then we run the same function with the 0. With the 0, this don't get evaluated because this doesn't work, so we print out 0. And then we discard this function, this execution context, we run out of it, and we continue the previous function where we stopped, which was here. It would be the same as if I called function from a function. B1, A, B2. B1, then I call A, and when I exit the A, I continue. This is the same. So when I exit, this function, which is accidentally the same function, accidentally, I continue here with the value of the param, which is 0. Then I exit this function here, but here at this point, param was 1 because it's a different stack, always creating new and new stack. So how does Fibonacci works? Let's say I want to have Fibonacci 1. Okay. Unexpected end of input. I'm missing this here. It becomes 1. counting first, I'm getting 1. Okay. I'm counting 2, I'm still getting 1. Now I'm counting 3. I'm counting 3, and 3 says it's Fibonacci 2 and Fibonacci 1. Fibonacci 2, so this runs first, which is the Fibonacci 3, and we have to compute Fibonacci 2 and Fibonacci 1. So this Fibonacci runs, it returns 1. This Fibonacci runs, it returns 1 as well. We do the addition, we get the result, which is 2. Okay, this is getting weirder. So we want Fibonacci 4, so we run Fibonacci 4. This doesn't happen. It says it's a Fibonacci 3, so Fibonacci 3 runs. Fibonacci 3 says it's Fibonacci 2 and Fibonacci 1. And as it's ending, there's still this plus. So this has to be evaluated as well. So when we run Fibonacci 4, it runs Fibonacci 3, and it has to run Fibonacci 2 as well. Because Fibonacci 3 comes here and says it's... I hope you're getting the flow. So Fibonacci 4 will call, come on, Fibonacci 3 plus Fibonacci 2. This is what Fibonacci 4 will call. So Fibonacci 3 is called from here. It calls for Fibonacci 2 plus Fibonacci 1. So then this is called, this Fibonacci 2, which returns 1 from here. Then it goes back, asks for Fibonacci 1, which returns also 1. Then this goes back, and we have to deal with Fibonacci 2. Again, Fibonacci 2 returns 1. This is why we have 4, 3, 2, 1, 2 here. Because again, this gets immediately called. So this doesn't happen yet. This gets immediately called. So we're calling Fibonacci 3, which is technically this, but this gets immediately called, which is Fibonacci 2. It ends, it doesn't call anything else, it just returns 1. So this gets called, it returns 1, and we've evaluated this. This is the same. So this gets called, which is Fibonacci 2. I'm hoping it's making a little bit of sense. So what's going to happen if we do something like Fibonacci 5? So we have Fibonacci 5, which is Fibonacci 4 plus Fibonacci 3, which means we need Fibonacci 4, which is Fibonacci 3, plus Fibonacci 2, which means we need Fibonacci 3, which is Fibonacci 2, plus Fibonacci 1, Fibonacci 2 is 1. So this gets evaluated. It doesn't continue here. I just return it from here, so the function stops here. So I ended this one, which is this one. I have to continue here. Fibonacci 1 returns 1, so I have this evaluated, which is Fibonacci 3, this Fibonacci 3, and I have to evaluate again Fibonacci 2, which is 1. So this gets evaluated because I can actually sum those things up. Yeah, I think yeah. So this gets evaluated. This is this one. So now I have to again compute Fibonacci 3, continue this sum. We already know that Fibonacci 3 is this. Fibonacci 2 plus Fibonacci 1 is this. So let's see if this is actually correct. 5, 4, 3, 2, 1, 2, 3, 2, 1. It's actually correct. So this is the flow of a Fibonacci sequence when using recursion. It actually looks simpler than the whole shifting of the partial n1 and 2. We just do what we're told to do through the formula. This is the formula for Fibonacci, so let's do it. The computer does it for us. It creates stacks for every execution. It creates execution contexts, and then it just exits and continues. So when it runs into this, it has to evaluate it first up to here, and then it starts to evaluate this from here and continues. Because when I run the Fibonacci here, this Fibonacci is called, and when this Fibonacci ends, it continues. It needs to add this Fibonacci. So this is the core of recursion. I'm going to give you another example of recursion. Why recursion? It looks simpler, but it may be harder to grasp. Recursion is great when you're working with a set of data. I'm not going to write any code that would actually work. We don't have the tools for it yet, but you will, for example, get the idea. You know that on computer, things are stored in folders and files. So you have folders, and within folders you can have folders and files. So let's say we have some sort of start folder, some path. Let's say we have a function get files that returns the files or everything, and we have function is directory that can say whether the item is list all items from path. Check if item is directory. And let's say you want to list or you want to do something, some action on everything in that path. So not just directly in that path, but in every single subdirectory that belongs to the path. So in this case, if I would run it, for example, on the recording, I want to run it on those two folders, and I want to run it on all those things in all those folders over and over and over again to any level down. So what I can do, and I don't know where the level ends. I have no idea where the level ends. But what I can do would be, for example, do stuff on the path. What I could do is something like this. So let's get all the items within the path. And then go through all items, and if is directory item, then do stuff on that item. Else, for example, just console log the item and just write everything. So what would happen is, okay, let's say I have this structure, I have my path, and here I have file 1, file 2, directory 1. In the directory 1 I have file directory 1, file directory 2, I have file 3, I have directory 2, and then I have file say I have structure like this. This is my structure. So I read all the items, which is file 1, file 2, directory 1, file 3, directory 2. So I just console log this one, console log this one, and I figure out, okay, this is directory. So let's get item in this directory. This is file, I just output them. The recursion call to the do stuff finishes, so we continue here, we continue where we stopped, because the items is in different stack, the items is different. When we run the do stuff for the first time, the items contains this. When we run the do stuff here, the items that is different in a different stack will contain file 1 and file 2. So when we continue, when we end this, we continue. File 3 we just write out, and we say, okay, this is directory, so we have to do stuff on the directory. Let's list those two things. Okay, this is a file. Let's write it down. This is a directory, so let's do stuff on this directory. List this. This is a file. So let's just step it down. We step down from the directory. There's nothing else here. We step down from this directory. There's nothing else here. If there was something like this, here we would step down once, and the second time, and we would continue with the items in a different stack. I hope it makes some sort of sense, but this is doing this with some sort of while cycle or for cycle. It is possible, but it is much harder because you have to manage where you sort of are, what the connection is, how to get from here to here. That's the problem. When you're using recursion, the programming language does it for you because it manages the execution stack, it manages the scope stack for you automatically. It's what it does. Wait a second. Again, I need not copyrighted music to play. Again, if you wanna if you wanted to manage it for yourself, you would have to somehow here say, okay, now let's try to list item again. So there would have to be some sort of cycle that lists items when it's directory, and you would have to remember that this stack exists as well. You would have to do something like, I don't even want to write it because, well, that's annoying. You would have to be like, at the beginning, items is get items path, and then go through all items in a cycle, and if items is directory, you would have to do something like this, while true. As I said, I even don't want to write it because I'm not sure how. I would actually have to think about it. So while true, items, if it's directory, well, I would have to keep the stack, and we don't even have the way how to keep continuous data, multiple data at once. The stack, we haven't talked about arrays yet, so there would probably have to be some sort of array. You don't even know what it is, and I would have to push the existing items to the stack, and say path is the item. So let's redefine the path, probably continue here, so it would somehow jump here, go here, at the end of the go through all items, at the end I would somehow have to say, is something in A, in the array, in the stack that I would have to create? Well, if it is, let's say path is alt path, so I would have to actually have probably two arrays, one checking the path, one working with the stack, and I would have to say items, yeah, is in the, like, the last thing is last item in my stack A, drop the last item from the stack A, and continue here. Yeah, there would have to be another cycle to continue through what I haven't done yet. There would have to be actually several cycles within each other, so when I'm jumping inside a directory. When I get outside of the directory, I'm still working on the items that's in my stack. So I would have to recreate all those stacks together. It is possible. I'm not saying it's not possible, but this is easy. This is managing stacks and contexts where you are, where you have to continue. So when you enter this directory and you jumped out of directory, you knew you're here in the stack. The language does it for you, using the jumping within the function and creating and discarding execution context and stacks. So why do this when you can do this? So this is recursions. As I've said, this is one type of recursion. Technically, there is a different type of recursion, which would be function A calls B, function B calls A. It's still considered a recursion because when I run B, B runs A runs B, B runs A runs B. The same, this would run forever, of course, obviously. This would run forever. So in recursions, you actually have to manage that they should stop somewhere. At a certain point, there should not be any iterations anymore. Which is here in my Fibonacci when I'm doing and I'm calling the Fibonacci. At a certain point, I end the cycle. This would go forever. This would not even count anything, but would just go forever. Obviously, it wouldn't count anything. There are no seed numbers. But you have to manage that somewhere you have to jump outside instead of just calling forever. So this is about closure, references, and recursion. At this point, we know what we need to know about functions, and next time we can start with objects. Thanks for watching. Bronya is out.